Since kinematic mechanisms, fundamental definition, mechanism versus machines. Understanding the distinctions between a mechanism and a machine is crucial in mechanical design. Mechanism. An assembly of rigid or resistant bodies connected together in such a way that the motion of any one body causes a completely constrained and predictable motion in the others. Its primarily purpose is to transmit or modify motions. Example: a typewriter, slider, crank linkage, spring-loaded toy mechanical systems. Machine, a mechanism or a system of multiple mechanisms working together in addition to modifying and imparting specific motion to its components. A machine is specifically designed to transmit and transform available mechanical or thermal energy into useful directed mechanical work. Classification of constraint motions. Kinematics pairs display different behavior depending on how their physical geometry or external components limit relative motion. A completely constant motions. The relative motion between two components takes place exclusively in a single well-defined direction, regardless of the direction or magnitude of the externally applied force. A clear example is a square bar placed inside a perfectly matching square hole, or a circular shaft fitted with collars on the both sides inside a round bearing to prevent excess sliding. Successful constant motions. The natural physical geometry of the mating parts permit motion in more than one direction, but external means of forces restrict it to only one valid path. For example, a vertical shaft in a footstep bearing could theoretically slide vertically upwards or rotate. However, the external downward force of a load or gravity ensures it stays seated, allowing only rotational motions. Incompletely constant motions. The motion between components can occur in more than one direction, and the actual direction depends completely on the direction of the variable external force applied. A classic example is a simple cylindrical shaft inside a perfectly round matching hole without axial shoulders or retaining collars. It can spontaneously rotate and slide axially based on immediate external interactions. Materials and links, rigid versus resistant bodies. Rigid body, an idealized structures body that suffer absolutely zero macroscopic distortion or deformation under any magnitude of working external force. Resistant body, the real world material that are not perfectly rigid but behave as completely rigid bodies for specific operational purposes. They serve, for instance, a flexible belt drive is completely flexible under compression but acts as highly effective rigid link when subjected to pure tensile operating forces. Kinematic link element, a functional member or a combination of rigidly attached members forming a part of a mechanism that possesses clear relative motions with respect to the other components. Links are structurally categorized based on their connective nodes. Binary link has two connection nodes, terminal link has three connection nodes, quaternary link has four connection nodes. Classification of kinematic pairs according to the nature of contact. Lower pair, the two elements share an extended surface or area contact during relative motion. Example: a sliding piston inside a cylinder, a knot turning on a thread screw, or a journal rotating in a bearing. Higher pair, the mating elements share only a theoretical line or point contact during relative motion. Example: a cam and a follower assembly, or a wheel rolling smoothly along a flat road surface. According to the nature of mechanical constraint. Closed pair. The pair links are held together by geometric or physical constraints. They can only be uncoupled through the mechanical deformation or structural destructions of at least one component. All standard lower pairs are naturally closed pairs, open or unclosed pair. The links remains in contact due to an active external source, such as the continuous force of gravity or an international preloaded spring configuration. Example: standard ungrouped cam and follower system. According to the nature of relative motions, pair type, relative motion description, standard engineering examples. Sliding pair. Pure linear sliding reciprocating or relative motion, a rectangular piston inside a matching guide group, turning pair, pure rotational or revolving relative motion about a single axis, a circular shaft turning smoothly inside a journal bearing, a rolling pair, one element rolls over the surface of another without slipping, ball and roller bearings or a wheel on a rail track, screw helical pair, spontaneously turning and axial sliding motion linked via thread pitch, the lead screw and matching knot assembly of a lathe machine, spherical pair, spherical rotation about a fixed pivot point in three dimensions, a ball and socket joints assembly, example car suspension pivots, joint analysis and mobility criteria. When multiple links are joined at a single node, the intersections is classified based on equivalent binary joints. Binary joint, exactly two links are connected at a single node. Ternary joint, exactly three links are connected at a single node. It is analytically equivalent to two binary joints. Quaternary joint, exactly four links meet at a single node. It is typically analytically equivalent to three binary joint. General joint reduction rule: if n links intersect at a single mutual kinematic joint node, the intersection is equivalent to exactly n minus 1 binary joints. Three-dimensional space mechanism mobility: for a generalized spatial mechanism operating in 3D coordinates, the total mobility or degree of freedom is calculated using f is equal to 6 whole l minus 1 minus 5p1 minus 4p2 minus 3p3 minus 2p4 minus 1p5, where L is the total number of physical links and PF represents the count of joints possessing exactly an individual degree of freedom. Planar two-dimensional mobility कुछ batch on Grubler criteria. For a planar mechanism, every unconstrained link moves within 3 planar degree of freedom. Pin joints, lower pair remove 2 degree of freedom while higher pairs remove 1. This gives Kurzweil's mobility equation F is equal to 3 whole L minus 1 minus 2J minus S, where L total number of link in planar setup, J total number of single degree of freedom binary joint pin or single sliding joints, H total number of higher pairs point line contact joints. Grobler's spatial equations for a mechanism designed to provide exactly a single degree of freedom, F is equal to 1 and containing 0 higher pairs, H equal to 0. Kurzweil's equation simplifies 3L minus 2J minus 4 is equal to 0. This implies that a valid 1 degree of freedom planar mechanism must always consist of an even number of links, with 4 being the absolute minimum requirements. L is greater than or equal to 4. Interpreting degree of freedom values: F is equal to 0, the arrangement is a rigid frame or structure, no relative motion can occur. F less than 0, the arrangement is a highly over-constrained, statically indeterminate structure, often termed a superstructure or redundant frame. F greater than or equal to 1, a kinematic steady mechanism, and F is equal to 1 configuration require exactly one independent input variable to produce a fully predictable constant output. Kinematic chains and Grasshopp's law. A closed loop of links forms a kinematic chain if the resulting relative motion are completely or successfully constrained. If the loops is completely locked against any internal motions, its function as basic structures. Grasshopp's mobility law for four-bar mechanisms. Grasshopp's criterion predicts whether a four-bar linkage can achieve full rotatability based on the length of its links. S plus SL is less than or equal to P plus Q, where S length of the absolute shortest link, SL length of the absolute longest link, PQ length of the remaining two intermediate links. Analysis of Grasshopp's case. Strictly case 1: S plus SL less than P plus Q. If the shortest link S is fixed directly to the frame, the mechanism operates as a double crank mechanism, allowing both adjacent links to make full 360 rotations. If either link's adjacent to S is fixed, the setup acts as a crank rocker mechanism. The shortest link rotates fully, driving the opposite link to rock back and forth. If the link opposite to X is fixed, the configuration function as double rocker mechanism. Case 2: equal linkage S plus SL is equal to P plus Q. If all links have distinct lengths, the motion pathway matches case 1. Parallelogram linkage configuration: S is equal to P and SL is equal to Q. Fixing the shortest link S or the longest link SL creates a highly efficient crank double rotation system. Deltoid linkage kite configuration: fixing S creates a crank system while fixing SL yields a crank rocker system. Case 3 is class 2 linkage S plus SL is greater than P plus Q. Grashopp's law is completely unsatisfied. No single link can perform a full 360-degree rotations, creating a pure rocker mechanism regardless of which link is chosen as a fixed frame. Kinematic inversions are of standard mechanism. By fixing different links in a kinematic chains, we create distinct mechanism with unique motion profile. This technique is called kinematic inversion. Inversion of a single slider crank mechanism. A standard slider crank mechanism uses four links, one frame, one rotating crank, one reciprocating connecting a rod, and one slider. It contains three turning pair and one sliding pair. Fast inversions link one frame or cylinder is fixed. Used in conventional reciprocating internal combustion engines and reciprocating pistons or air compressors. Second inversion link to crank is fixed, used to drive the Whitworth quick return motion mechanism and classic multi-cylinder rotating radial aircraft engines. Third inversion link 3 connecting rod is fixed, the use in crank and slotted lever quick return mechanism insulating cylinder system engines assembly. Fourth inversion link 4 is piston slider is fixed, used in structural manual hand pumps and heavy bull engines setup. Inversion of a double slider crank mechanism. This configuration contains four links arranged with exactly two turning pairs and two sliding pairs. Fast inversions link one slotted frame is fixed, creates an elliptical trammels, an instrument designed to trace mathematically perfect elliptical profiles. Second inversion slider 2 or 4 is fixed, generate a Scotch yoke mechanism which converts pure uniform circular motion into smooth in sinusoidal linear reciprocating motions. Third inversion link 3 connecting link is fixed, generate the Oldham coupling used to transmit torque between two parallel shafts that have a small lateral offsets. Mechanical advantage and toggle position. The mechanical advantage of a mechanism is the ratio of the output force to the input force. Assuming a highly efficient system with negligible friction losses, power balance gives P input is equal to P output T2 omega 2 is equal to T4 omega 4. Therefore, the instantaneous mechanical advantage can be expressed as MA is equal to T4 by T2 is equal to omega 2 by omega 4, where omega 2 is the input angular velocity, omega 4 is the output angular velocity, toggle position, and infinite advantage. When the transmission angle gamma between the coupler link and the driven output link reaches exactly 0 or 180 degree, the output angular velocity omega 4 drops to 0. As a result, the instantaneous mechanical advantage approaches to infinity. This extreme boundary layout is called toggle positions. It is widely used in high load industrial clamping mechanisms, stone crushers, and heavy duty stamping presses to exert massive forces with minimum input torques.